All right, let's dive right into the secret world of biologic drugs. Now, these are not your everyday pills. They are seriously powerful, super complex therapies that have completely changed medicine. And in the next few minutes, we're going to uncover their incredible journey inside the human body.
So, picture this. On one side, you've got something like aspirin. It's small, it's simple, you swallow it, and your body pretty much knows the drill. But on the other side, you have biologics. These things are enormous proteins that have to be injected. They are a totally different beast, and they play by a completely different set of rules.
So here's the roadmap for our masterclass. We'll start with what makes these drugs so different. Then we'll see how they get in, how they move around the body, we'll uncover the secret to why they last so long, and finally, what happens when your body decides to fight back.
Right, so like we said, we're not talking about your standard, simple little molecules here. Nope, these are huge, engineered proteins, built to hit very specific targets in the body, which is exactly why their journey is so unique.
Okay, so if these are giant protein molecules, how in the world do we get them into your system so they can actually do their job? This brings us to the very first challenge, the entry point. It's the first question anybody would ask, right? I mean, if you can pop an antibiotic, why can't you just swallow one of these?
And the answer is actually really simple. Because these drugs are proteins, your stomach would look at it and think, oh, lunch. It would treat it just like a piece of chicken, the acid and all those enzymes would just tear it apart, making it totally useless before it ever got a chance to work.
So, we have to find a way to completely bypass the stomach. The first option is an IV, right into the vein. That gives you 100% of the drug, boom, straight into your blood. The second way is a subcutaneous injection, just under the skin. And this route, well, it's surprisingly slow because the drug has to take this long, winding detour through your lymphatic system first.
And just how slow are we talking? Get this. It can take anywhere from 1 to 8 days for that drug you injected to hit its peak level in your blood. That is a world away from the instant hit of an IV.
Okay, the drug is in the system. So where does it go? And how does the body start trying to get rid of it?
Well, because these molecules are so big and hydrophilic, which is just a fancy way of saying they love water, they pretty much stay put. They just hang out in your bloodstream and the fluid right around your cells. They're too big to just wander off into other tissues like your brain.
Now, your body has two really different ways of cleaning these drugs out. The first is a slow, constant process where your cells are just kind of sipping on the fluid around them and breaking the drug down. But the second way, target-mediated disposition, that is way more dramatic. The second that drug finds and binds to its target, the whole complex gets a giant red flag, and the body removes and destroys it immediately.
And that brings us to what is, for my money, the coolest part of this entire story. If the body is always trying to clear this drug out, how on earth can a single dose last for weeks? Well, it all comes down to a brilliant little recycling secret. Seriously, think about that. Many of these drugs have a half-life of around 21 days. That seems impossible when you know cells are constantly trying to eat it. So what's the trick?
Let me introduce you to the hero of our story, the neonatal fuck receptor, or FcRn. You can think of this little protein as a master recycler. Its whole job is to rescue these valuable drugs and save them from being thrown into the cellular garbage disposal. So here's how this amazing rescue mission works. First, a cell swallows the drug. Inside this acidic little bubble, the drug latches onto an FcRn receptor, which is basically its VIP pass. Instead of getting sent to be destroyed, the FcRn acts like a personal bodyguard, escorts it right back to the surface, and releases it back into the bloodstream, totally safe and sound. And this incredible rescue and recycling system is the entire reason patients can go 2, 3, sometimes even 4 weeks between their doses. It's just a beautiful piece of biology that modern medicine has learned to take advantage of.
But the journey doesn't always go so smoothly. Sometimes the patient's own body looks at this amazing, life-saving drug and sees an enemy. And that brings us to our final chapter, when the body rebels.
This rebellion takes the form of something called anti-drug antibodies, or ADAs. What's happening here is your own immune system gets confused and literally starts making its own antibodies designed to hunt down, attack, and neutralize the very medicine that's supposed to be helping you. And you've got two main types of these troublemakers. You've got binding ADAs. They just kind of glom onto the drug, making big clumps that the body gets rid of much faster. But then you have neutralizing ADAs, and these are way worse. They attack the drug's active site, basically turning it off completely.
And this isn't just some textbook problem. This quote right here describes a heartbreaking reality for patients called loss of efficacy. Someone is doing great on a drug for months, and then it just stops working. And when the doctors check their blood, the drug is just gone, wiped out by these anti-drug antibodies.
Which leaves us with this final massive question. The secret life of these drugs is this constant chess match between brilliant human engineering and our body's own incredibly clever immune system. And figuring out how to stay one step ahead, well, that's the future of this medicine.